associate professor at UT Austin. He's been working on imitation learning, reinforcement learning, and a bunch of other things as the PI of the Personal Autonomous Lab. Scott has got multiple awards. He got the NSF Career Award. He got a Young Investigator Award, and even a teaching professor at UT Austin. He's been working on. Sorry, I think I had the YouTube video playing somewhere, so I was hearing my voice twice. Okay, so it's a pleasure to have Scott, and Scott, we'll let you take it away. I'm super excited to hear more about value-aligned learning.
Yeah, thanks so much. Yeah, so thanks everyone for having me. So like most roboticists, one of the primary goals of my work is to get robots out in the world doing useful things. And to do that, we're going to have robots that are customizable by end users, because we're going to want them to be able to do things like small manufacturing where the task constantly changes, or operate appliances that are a little bit different in everyone's home, or collaborate with people, all of whom have their own different abilities and preferences, etc. And so we certainly can't expect that we're going to be able to pre-program, at least not 100%, all the things that we want these sorts of robots to do. And for that reason, things like imitation learning have become really popular in recent years as a way of teaching robots just by showing them how to do tasks. And if we kind of do a rewind back to 2012, when I was doing my PhD, I developed some work where a series of algorithms that allowed me to show unstructured, unsegmented demonstrations of these sorts of like complex multi-step tasks like IKEA furniture assembly to a robot, and then essentially have the robot look at those demonstrations, pull out skills that it recognized that were shared across different demonstrations, learn controllers for each of them, learn to sequence them. And you can see there's a lot of vestiges of the time here, like, AR tags instead of doing real perception, et cetera. But this was very exciting and certainly, state of the art at the time. But as you probably know, if you've done much robotics, you should never trust a robotics video, right? Roboticists are always going to show you the best execution that the robot ever did. And, if you actually dig into our paper and look, this column here is essentially the number of human interventions that were necessary whenever the robot made a mistake during the task that needed to be fixed so that the robot could continue. And if you look, there was only one time when there were no errors. And of course, that's the video you saw, right? And that is not to condemn this work and say it's bad, it was bad work, or that imitation learning sucks, or, anything like that. It's just to say that, imitation learning is imperfect and unreliable. And the thing that bothered me at the time, and still now, is not that the robot made mistakes. Like, I think it's fine for robots to make mistakes. People make mistakes. But it's that the robot didn't really know when it was going to make a mistake. It had no sort of confidence about if it had learned the right thing or inferred the goal of the task correctly. And it really had no way of communicating anything about that to me. It just sort of blindly went ahead and executed. And you might think, well, okay, that's unfortunate, but maybe that doesn't matter, because maybe things are just so much better in 2021, so much more reliable, that we don't really need to worry about, robots that know what they know, or that, can tell you when they're going to fail. But that's not really the case. If we take a look at, a couple papers that were published in the last 2 years and look at success rate graphs, for some of the simpler tasks, we see like, 50% success rate, maybe as low as like 12.5. And, I blacked out the names of these papers and algorithms because I think these are actually very good papers. I'm not trying to, throw any shade on these. It's just to say that imitation learning is hard. And our algorithms are imperfect. And, these are much harder tasks than what maybe, we were doing 10 years ago. They're from, just straight from pixels, and sometimes it's one shot, but it's unreliable. And I would argue that perhaps this metric of success rate is just the wrong metric to begin with. I would rather have a robot in my house that can only perform 50% of the tasks I show it, and the other 50% of the time just says, I don't think I can do that, or I don't have enough data. I would much rather that than a robot that performs, can perform 90% of the tasks, but then just kind of fails randomly 10% of the time silently, and that could do something, very wrong or even dangerous. And so if we're going to have robots that look more like that second case, we really run up against, what's being referred to as the value alignment problem. So one definition of value alignment that I like is that highly autonomous AI systems should be designed so that their goals and behaviors can be assured to align with human values throughout their operation. And I like this definition because it calls out two different possible sources of error that I think are really important to separate. One is error from behavior. So, if you, like in a reinforcement learning setting or given a reward function, this is what you're supposed to, optimize. Can we evaluate how, can the robot, itself evaluate how good its behavior is with respect to that? And sure, we have a huge literature on how to do this from formal methods, safe reinforcement learning, et cetera. So this is a really well-studied area and source of error. But what about goals? Do we have algorithms that allow the robot to look at demonstrations, for example, and reason about how sure it is that it has correctly inferred the goal of the task? And it turns out that there is like a staggeringly small literature on this, and that by and large, the thing that's missing is performance guarantees, like hard statistical performance guarantees that we would want in order to really trust a system like this. So this is what I'm going to be talking about today, is focusing on the goal aspect of value alignment. So just a quick refresher in case you're not super familiar with these areas. So first, I'll start with sort of the simpler imitation learning case. So we're going to be given some reward function that in the simplest form just maps states to scalar rewards. The agent's going to take actions, which takes it from some state to some next state, and you get a sample of reward. And it's trying to learn how to learn an optimal policy pi star, where a policy is just a mapping from states to distributions of actions. And by optimal, I just mean that it in expectation is going to get the highest sum of rewards, which we call return. And in general, the way that we measure the value of a policy, pi, with respect to some reward function r, is just going to be this expectation of summed rewards when we execute policy pi, and they're discounted by a discount factor. Okay, so what about the imitation learning case? This is going to be a little different. Instead of being given a reward function, there's just sort of a reward function that's implicitly in the demonstrator's head. And the standard assumption that's made in imitation learning is that the demonstrator is then going to act near optimally with respect to that reward function, which is going to produce some demonstrations tau. And these demonstrations are now what the robot sees rather than samples of state and reward. So it doesn't get to see anything about reward directly. And then it can do one of two things. It can take a supervised approach like behavioral cloning, where it really just tries to use these demonstrations to learn to map states to actions in a supervised manner. This typically doesn't generalize well outside the set of states that was seen in the demonstrations. And so this is not the approach I'm going to talk about today. Instead, what I'll be talking about is inverse reinforcement learning, where we look at these demonstrations and the robot tries to identify, what's the reward function that caused the person to behave this way in the first place. In other words, can I come up with a reward function that makes these demonstrations look approximately optimal? And once I have that, you can just use RL and learn an optimal policy with respect to that. Okay, so then that brings us to what we in my lab have been calling the value-aligned imitation learning problem. So at a high level, what this is I want to be able to give some demonstrations to a robot and have it, think for a while, maybe practice a little bit, and come back with one of two answers. It either comes back with a policy and says, hey, even though I don't know the ground truth reward function that was in your head, I still think, I have probabilistic confidence that I am almost as good at this task as you are under your hidden reward function. Or it comes back and says, I don't have enough data. I can't really make any guarantees about my behavior. So this is hard, right? Because now we're not just dealing with like that behavioral uncertainty of like, how well would a certain policy function under a particular reward function? We're saying, how well would the robot's policy that it comes up with, function under like the whole distribution of reward functions that could have been true given the demonstrations we saw. So this is a quite tricky problem. So specifically, what we're really trying to do is we're trying to upper bound the policy loss, the difference between the value of the robot's policy under the true reward and the value of the policy that's optimal under that reward within some epsilon with high probability 1 minus delta. So how are we actually going to do this? Well, that's what the talk's going to be about today. And it's going to be in two parts. The first part is going to be looking at challenging poor statistical assumptions that have historically been made in imitation learning so that we can first come up with a data-efficient algorithm, but that's computationally intractable. And then we'll examine how to deal with the computational tractability issue as well. The second part of the talk is going to acknowledge that we can only get so far by improving sort of statistical learning methods. And that, my belief is that if we really want to kind of get all the way to almost, human-like imitation, we really need to leverage data modalities that have been historically underutilized that people often use when they're learning. Things like looking at someone's gaze when they're teaching something, or their facial expressions, or using, contact and force data. So that'll be in the second part of the talk. Okay, so first, just a little bit of background on inverse reinforcement learning. So, this idea goes back to around like 2003, 2004. And in general, we have some demonstrations, tau 1 through tau n. And we are going to typically make the assumption that reward is linear in features of state. And we can make this assumption without loss of generality because these features phi can be arbitrarily nonlinear functions of state. And so by linearity, what I mean is just that the reward at a given state can just be written as some weight vector w, which parameterizes a reward function, dot these features phi. Okay, and our objective is to find this weight vector w, or a reward, in other words, that makes the demonstrations look optimal. Okay, so one of the nice things about the linearity assumption is that we can now write the value of a policy in a really simple form. We can just write it as w dot what we're going to call mu of pi, which are the feature expectations of pi. In other words, the sum of discounted features we're going to see along trajectories when running policy pi. And the reason it's useful to write the value of the policy in this way is because the standard approach to inverse reinforcement learning is to find a reward function whose corresponding optimal policy has feature expectations that match those of the expert. Why is that? Well, because if we match the feature expectations, then we're under any reward function, we are guaranteed to match the value of the policy. But in general, we cannot exactly match the expert's feature expectations. One reason is because we actually don't even know what the expert's feature expectations are. We only have samples from their policy. We don't know the exact feature expectations. And so there is one existing bound that sort of solves, or is, I guess you could say, I think it poorly solves, but that solves the value aligned imitation learning problem, which is here. And it's a bound that says, if we want to make sure that our policy loss is bounded by some epsilon with probability 1 minus delta, it suffices to have some number of M demonstrations. And I won't get into the details of the bound here, but this is sort of a like Chernoff-Hufting style, concentration bound. And the assumption that a bound like this is built on is essentially a worst case or sort of adversarial assumption that if we come up with a policy and we think we're matching the estimated feature expectations of the expert, but we're off from the real ones a little bit along some dimension, along some feature. Maybe there's some adversarial reward function out there that could kind of throw all its weight toward penalizing us as much as possible for being off in that feature dimension. And that would be really bad, right? But this seems a little bit fishy because this can be any reward function at all. It doesn't have to be a reward function that agrees with the data at all. You could have a bunch of demonstrations that avoid lava, and then you say, but what if it was really good to jump in lava, right? Like that seems a little bit ridiculous. So can we do better than worst case? The standard assumption is that worst case reasoning is kind of the best thing we can do if we don't know the ground truth reward function. And I'm just going to suggest what I think is a very sensible alternative, which it seems like it could perhaps be much more efficient to consider the likelihood of reward functions when we're assessing risk. Okay, so to do that, we're going to need two existing tools before I get onto our algorithm for doing this. The first tool is going to be an IRL algorithm that gives us a posterior distribution over reward functions instead of just a point estimate like we've seen before. And we're going to need a risk metric. So to get that posterior distribution, one tool we can use is Bayesian inverse reinforcement learning. So the idea here is instead of having a point estimate of reward, we're just going to use MCMC to sample from the posterior distribution of reward functions. And the main term we're interested in here is this likelihood, where we basically say that the likelihood of the demonstrations given a particular reward is equal to this sort of Boltzmann or softmax probability, which basically just says, we think that the demonstrator is quote unquote Boltzmann rational, that they take better actions exponentially more often than they take worse actions under this reward function. And if you know a little bit about RL, this can be written in terms of the Q star function, the optimal Q function with respect to the reward R. Okay, so that's what we're going to use to get a posterior distribution of reward. We also need a risk metric, and we're going to use something that's called the alpha value at risk, a metric from the finance community. And the basic idea is that for some given value of alpha, let's say 0.95, the 0.95 value at risk is essentially the dividing line between the worst 5% of outcomes and the best 95% of outcomes. So it's sort of measuring this cutoff before the really nasty tail behaviors. Typically, you don't know the functional form of this outcome distribution. You just have samples from it. So you also would typically want like a single-sided confidence bound to go along with this that relates the number of samples N you have to your confidence. And what that allows you to do is to make statements following the finance analogy, for example, of the following form. With high confidence, you won't lose more than $500 95% of the time when you're using this investing strategy. And it turns out these types of statements are exactly the kinds of statements we're going to want for the value-aligned imitation problem. Okay, so I'm going to now present some of our work, which is going to be kind of a simple first cut at this, that I'm going to argue is a very data-efficient algorithm, but unfortunately computationally intractable. And we're going to come back and fix that intractability later. So what we're going to do is we're going to take our demonstrations and we're going to perform Bayesian inverse reinforcement learning, which will give us, a bunch of samples from the posterior distribution of reward functions. We're going to take our estimate of the map reward function, the maximum a posteriori, basically our best guess as to what the reward function really is. And we're going to solve for the optimal policy with respect to it that I'll call pi star map. This is the policy we're going to run. We could choose any other policy. It could even be a policy handed to us, but this seems like a reasonable choice. We're also, and here's where things get really intractable, for every other reward sample, RI we get, reward function sample, sorry, we're also going to solve for the optimal policy with respect to each of these reward functions. So if we get 1,000 samples from MCMC, we're solving for 1,000 optimal policies, which obviously is wildly intractable given that in robotics, it can take hours, days, weeks of data to solve for even a decent policy, under a reward function. We'll come back to this. But just for now, let's assume we can do this. And now what we're going to do is we are going to take these reward and policy pairs, and we're going to use them to compute a distribution over policy losses. And what this means is, remember, we're going to execute pi star map. And basically we want to ask the question, what if we were wrong? What if our map wasn't really the true reward function in the person's head? What if it was one of these others drawn from this distribution? How badly could we be doing then? So for each other reward function RI that could have been true, we're just going to ask the question, how bad would our policy do compared to the policy that's actually optimal under reward function RI? We do that for all the RIs, and that gives us a distribution over policy losses. We can then take that distribution, we can compute the value at risk with respect to it, we can put a single-sided confidence bound on it, and then, let's say we wanted to do this at like a 99% confidence level, we have some risk level that we consider acceptable or unacceptable. And now the robot has all the information it needs to say, hey, I think that with high confidence that most of the time I am almost as good at this task as you are. Even though I don't know exactly what the ground truth reward function is, I can bound the risk. Or the robot's going to come back and say, I don't have enough data. I actually can't make a high confidence guarantee that is like within the error bounds that you find acceptable. So that's great. That's exactly where we wanted to get. But what do we do now? Like, what if the robot does come back and say that it needs more data? Well, we could just give it more demonstrations, but that's a lot of burden on the human because, well, it's annoying to give lots of demonstrations, but also they're not going to necessarily know exactly what kinds of demonstrations to show and in what conditions to kind of fill in the robot's gaps of knowledge. And so I can't get into them today, but we do have 2 papers on both an information theoretic and a risk-based criteria we've developed for doing active learning to query the human in very particular ways that can sort of very quickly reduce the robot's uncertainty. Okay, but for now, let's just look at the non-active learning case. And as I mentioned, this algorithm that I presented is very computationally intractable. So we've only done this on very small problems, like little, discrete navigation problems, for example. But there's one really interesting property that I want to point out. So without getting too much into the numbers here, what we're going to be looking at is R bound at a 95% confidence level on top here. And we're going to be comparing with that worst case bound, which is the only other bound of this form that we know of on the bottom row here. And the 2 numbers that are of interest are here. And it's just to show that our bound on the policy loss, we can get just as tight with a single demonstration as the worst case bound can get with 23,146 demonstrations. And so this is more than 4 orders of magnitude more data efficient. So this goes from pretty much a completely vacuous bound that is not useless towards something that could really start to be used, in something like robotics. Like, people are definitely willing to give 1 or 5 demonstrations. They're definitely not willing to give this many. But of course, as I mentioned, this is computationally intractable. We could never scale this up to a real robotics problem. So we need to fix that. So that brings us to part 2 of part 1. Dealing with computational tractability. Okay, so it turns out that while we were trying to deal with this computational intractability problem, we kind of had to go back and really go back to the basics of inverse reinforcement learning. And we found 2 problems that that I think are really core to inverse reinforcement learning that I think we sort of solved along the way, which is an exciting little, side note of this work, I think, or maybe even it's the most important part. One of the problems is that, as I sort of already alluded to, virtually all inverse reinforcement learning algorithms in one form or another have some type of policy learning or like inference time data collection in the inner loop. There's methods like Bayesian REL that propose a reward function and learn an optimal policy and kind of have to keep, or an optimal Q function, and have to keep going back and forth doing this. Or more modern methods like generative adversarial imitation learning that does a little bit of a reward update step, a little bit of a policy update step. But no matter what, if you're doing this on a real robot, while it's thinking and trying to figure out what the reward function is, it's doing a bunch of stuff in the world. And it takes quite a lot of data, and that's not ideal. Second problem is a little more philosophical, and it's that standard IRL algorithms cannot significantly outperform the demonstrator because these algorithms assume the demonstrator is near optimal. And they're trying to do something like match feature expectations. So if the person makes a mistake, you're going to copy that mistake essentially when you match the feature expectations. This flies in the face of the story that we try to tell about IRL, that like it's inferring the intent of the demonstrator. But it really doesn't, at least not in the sense that humans do, where we're really good, even very small children, at not copying mistakes, for example. And I'm going to suggest that the underlying cause of both these problems is this near optimality assumption that IRL makes. And I'm going to suggest instead that perhaps we should allow there to be suboptimal demonstrations. And that if we just know a ranking over them about which ones are better than others in sort of a pairwise sense, that we can actually solve both of these problems at the same time. Okay, so our method for doing this is called trajectory ranked reward extrapolation, or TREX for short. And here's the basic idea. Imagine that I show you some demonstrations in Pac-Man, let's say, and you notice, and I give you a ranked order over them. I say, this one is better than this one, this one's better than this one. And you notice a trend that as the demonstrations get higher in rank, I seem to eat food more or eat more food and get caught by ghosts less often. And let's say, that I never performed anywhere near optimally in Pac-Man because I'm not very good at it. It's a hard game. But, you might extrapolate and say, well, okay, I see the trend in what's getting better here. I'm going to try to learn a policy where I never get eaten by ghosts and where I eat as much food as possible, right? And in that way, sort of extrapolate beyond the performance that you saw in the best demonstration at training time. And so in other words, we'd like to learn a reward function that discovers that trend, that respects the ranking, that if we graph the true performance of a trajectory, which is, a dot here, versus the predicted performance, we'd see kind of like a straight line, or at least like a monotonically increasing curve. And we hope that that, trend holds for trajectories that are much better than those that were seen at training time. And one really nice thing about framing things in this way that has to do with ranking is that it allows us to convert what was before this nasty, like back and forth optimization into just a fully supervised problem, that has no policy learning, no real-time data collection in it. I should say no policy learning at reward inference time. You still obviously have to run RL on the final reward function that's output. And here's how we turn it into a supervised learning problem. We just treat it as pairwise classification. We basically say that if a trajectory J is better than some other trajectory I, it should get more reward assigned to it, state-wise rewards. If you assign reward to every state in a trajectory and sum it up, the trajectory should have more total reward assigned to it than the worst trajectory. So in other words, you can say that the probability that one trajectory is better than another is related to this, sort of exponentially related to the amount of reward that they're each assigned. And you can just then stick that probability into any sort of classification loss you want. You can use, like, we used a cross entropy loss, for example, binary cross entropy loss. And thus it's just a fully supervised learning problem that's pretty simple to set up. And it turns out that with some kind of creative data augmentation and things like that, this is really the first IRL approach that works stably on like really high dimensional problems like Atari, and with about like 10 demonstrations. And I'll show some examples of this in a minute. Oh, and yeah, you know what, actually this last point I'm going to come back to in a minute. Okay, so how well does T-REX work? Here's just a sort of high-level illustration. Here's 3 demonstrations in increasing order of goodness that we give in the half-cheetah domain, where you're trying to learn to run as far as possible. And you can see that even the best demonstration is not very good. And we put it through T-REX, learn a reward function, perform RL on top of it, and you can see the T-REX is able to learn this nice coherent run that is significantly better than the best demonstration, and sort of extrapolates that trend that it saw in the demonstrations. Similarly, we get similar performance in higher dimensional problems like Space Invaders, for example, where T-REX discovers a policy that gets more than double the score of the best demonstration. And a bit more quantitatively, what we see is that across other sort of physics-y based domains like half-cheetah and hopper, if we compare T-REX in green here to the performance of the best demonstration and 2 other state-of-the-art imitation learning algorithms, behavioral cloning from observation and generative adversarial imitation learning, almost across the board, T-REX significantly outperforms both the competing algorithms and always significantly outperforms the best demonstration, and at times comes very, very close to equaling the performance as though we had just known the ground truth reward function up front in the first place, which is quite impressive, I think. And it turns out that these differences are just even more pronounced in really high dimensional problems like Atari games.
Scott, maybe a question?
Yes.
So for these different environments, you need to generate rankings in some specific way, or can you follow the same method to rank trajectories across games or across environments?
Yeah, I mean, so the ranking is just done by the demonstrators. I mean, they kind of look at the trajectories and just estimate which one is better, and where better is defined as having higher total return. Now, it's interesting that it is not clear that that's actually how people rank. And so we actually have a project going now where we're trying to understand, like, what do human preferences really mean? But as long as you can get people to give those sorts of rankings, then it works. But this segues nicely into my next point, which is you might say, okay, well, this is all nice, but this is not the standard imitation learning setting. Normally you don't have access to rankings. So the question is, can we do well without rankings? So we have another paper that's an extension to T-REX called DREX, which stands for disturbance-based reward extrapolation, where we auto-generate rankings. So we start with just a pile of unranked demonstrations, and we first just perform supervised behavioral cloning, which gives us this policy PyBC. And then what we do is we start generating rollouts of PyBC. First, just running the policy. Then, as we go on, starting to add more and more action-wise noise until we essentially saturate and just become random. And so you can imagine, in expectation, as long as this behavior clone policy was better than random, which it certainly ought to be, these trajectories that we generate with more and more action-wise noise being added to them should get worse and worse in expectation until they saturate at random. And so this gives us an approximate noisy ranking over trajectories. And it turns out that by doing this, we can do almost as well as if we had just known the ground truth rankings of this original data set at the beginning. So this puts us back in sort of the standard imitation learning setting. Okay, so there's one more algorithm in this REX series of algorithms, because so far I've only talked about how to get a point estimate of a reward function. But to solve the value aligned imitation learning problem, we actually need that whole posterior distribution. So can we do something that looks like Bayesian IRL, but that's actually computationally tractable using some of these ideas? And we can, and this algorithm is called Bayesian REX. It operates in two phases. The first phase is a feature pre-training phase, whose goal is to learn a representation that's going to allow us to do really fast and accurate MCMC in the second phase. So here's how the pre-training phase works. We start with our ranked or auto-ranked demonstrations. And what we're going to do is essentially first just run T-REX. We're running T-REX not to really get a reward, but to start learning some features that we think are going to be useful for predicting a distribution of rewards later. But we don't want to overfit. And so we're going to use a bunch of other self-supervised losses as well. Things like predicting inverse dynamics or forward dynamics or time differences between samples. And the way that we're going to do this prediction is we're going to take this like second to last feature layer, and all of these different quantities we say should just be predictable with a single linear layer after them. So, each of these different losses gets a different linear layer associated with it. And so all of these different quantities should just be able to be computable as a linear combination of these features. And the reason is that the whole goal of this pre-training step is to learn a set of features that we think are going to be useful in a linear fashion to predict reward and to predict that sort of whole posterior distribution of reward. So once we have these features, we're just going to run each of these demonstrations through the feature extractor, sum up the features for the trajectory, and it's going to give us these pre-computed vectors that are the feature counts for each of the trajectories. And the reason we want to do this pre-computation is because it's going to allow us to perform MCMC very efficiently now. So for any given reward weight vector W that we sample, if we want to know how much total return it assigns to each of these trajectories, remember, all we have to do is take W dot this summed up feature vector. And that tells us exactly, just with a dot product, how much total reward it's assigning to that trajectory. And now we can have a likelihood function that kind of, looks like one of these softmax things we were looking at before that basically says, well, we should be assigning a good reward function is assigning more reward to trajectories that are ranked higher than trajectories that are ranked lower. That allows us to perform MCMC. We repeat it n times, we get samples from our posterior. And now, we can do this whole thing, but in a computationally tractable way. So now let's just put it all together. I think one of the most interesting illustrative examples we have of this is in an Atari game called Beam Rider. So Beam Rider is interesting because it has this property where if you don't press any buttons at the beginning of the game, the game looks like it's happening, like things move around on the screen, but the game never really starts. You can never get any score. And eventually, after something like 100,000 time steps, the emulator just times out. I'll come back to this in a second, and you'll see why this is interesting. So what we do is we give Bayesian REX some demonstrations, that are ranked, and then we ask it, can you basically tell me which of these policies, give me a ranking over these policies of how good you think they are. So policies A through D are just handcrafted policies we created that are, if we look at the ground truth score they get in expectation, the policies get better and better A through D. The no-op policy is a policy that never presses any buttons and therefore never gets any score. Okay. So if we ask Bayesian REX to tell us how good it thinks these policies are by just having it look at a point estimate of the reward, maybe the mean reward or the map reward. This is essentially equivalent to running vanilla T-REX and getting a point estimate. You'll see that it gets the ranking of A through D correct, but it gets no-op horribly wrong. It thinks no-op's the best of all. So why does it think that? Well, because if you think about in a domain like this, in general, and this is not always true, but in general, the better you do at the game, the longer you live. And so the trajectories, get longer and longer on average. So the simplest reward that could explain that ranking would just be +1 at every time step, right? But that's going to horribly overestimate how good the no-op policy is, because the no-op policy lives a very long time. But if instead we ask Bayesian REX to actually think about the whole distribution of reward functions and say, think about this in terms of value at risk. Now it gets A through D correct, but it realizes that no-op is very, very risky. I mean, maybe no-op's good, but the tail looks really bad, and it could be a very dangerous policy. So now we've kind of come full circle. We've done exactly the thing we want. Even for high dimensional problems, we're able to reason about the whole distribution of rewards that could be true, and we're able to reason coherently about risk in these domains. And this is just policy evaluation, but this idea is not restricted to policy evaluation. We have another paper that I don't have time to talk about today, but where we can actually learn policies that minimize risk as well. Okay, so this kind of concludes the first part of the talk, where I'm talking about statistical methods. And what I introduced was a framework that describes the value-aligned imitation learning problem. We showed efficient IRL methods that we can leverage to come up with both an efficient and a computationally tractable algorithm that allows us to reason about policy risk. And of course, now we're trying to, in my lab, to take this. I think we have all the core algorithmic stuff. We just need to make it happen now. We're trying to actually do this with real-world manipulation tasks. But in the second part of my talk, what I want to talk about is that I think to really get value-aligned imitation learning to happen on real robots in general, and with small amounts of data, we're really going to need to think about a lot of these data modalities that people often learn from, like gaze and facial expressions, that make learning from other people so rich, and figure out how to leverage them on robots. And so this second part of the talk is going to be at a much higher level than the first part. And it's really just to give sort of a broad overview of some of the different types of modalities we're looking at and how we use them. So one modality that we've been looking at a lot recently is human gaze. So it's well known from the cognitive science literature that gaze is extremely important in human teaching of tasks, both in kind of looking at like what the teacher is looking at, and also what's called mutual gaze, which has a very particular meaning in teaching, where two people look at each other. So we've been collecting gaze data in a variety of different ways. Sometimes we have people wear special glasses that track their gaze when they give demonstrations. Obviously, in the real world, these are not always going to be available to demonstrators. So we also have a computer vision algorithm that can track both where someone's looking and when they're in a condition of mutual gaze with the robot. So what can we actually use this gaze information for? So one thing it can be useful for is sort of resolving ambiguity. So if a person gives a robot this demonstration of placing a ladle next to the right of this yellow ball, if I showed you one demonstration of this task and then I mixed up where everything on the table is and I said, do it again, what would you do? Would you put the ladle to the right of the yellow bowl, or would you put it to the left of the red plate, or maybe exactly at the spot on the table where I placed it, right? From just a single demonstration, it's ambiguous. But if you take a look at where this person is looking as they're giving the demonstration, their eyes keep darting over to the yellow ball, which gives us a hint that that's the coordinate frame with respect to which the task is being performed. And so we have a paper on this and a lot of other insights we were able to sort of mine out of a bunch of gaze data we collected, and a very simple sort of proof of concept of how you can integrate this with inverse reinforcement learning. We've also been looking at how we can use gaze as what we call supervised attention. So if you think about a neural network that either has an attention layer, or even if we're just looking at like a sensitivity analysis shown here, like with a tool like GradCam, what we see is that algorithms like T-Rex often sort of miss very important, but sometimes like visually small features, like the ball in this game of Breakout. And we noticed that when a human's performing the task and giving demonstrations, they're focusing their gaze primarily on the ball, actually. And so we just add an additional auxiliary loss term that we call the coverage-based gaze loss, which just says, our learning algorithm should at least pay attention to the things that the human was paying attention to, essentially. It shouldn't try to match that attention, because people look at, they use their peripheral vision, they look around and remember where things are without actually looking back to them, et cetera. So we want to give the algorithm flexibility to look at whatever it wants, but we want to make sure we at least have coverage where the human looks. And it turns out that this makes algorithms like T-Rex actually perform significantly better. Another type of signal that we've been using is what we call implicit human feedback, signals from people that occur naturally, that they didn't necessarily intend to change the agent's behavior, but nonetheless are useful. And since they're naturally produced, we don't have to ask people for them. There's no extra burden on the person at all. So things like facial reactions, for example, when something goes well or goes poorly. Now, the flip side of this is that these signals are super noisy and really hard to learn from. So we have a system we've developed called EMPATHIC for learning from various types of implicit feedback, but here's an example of learning from facial reactions. So we first have a sort of training phase where we just have a person watch a very simple game being played by an agent. They're not in control at all. And there's these 3 different colors of blocks. They're each associated with a particular positive or negative monetary reward. And this is real money. So, when the agent picks up certain blocks, the person either makes money or loses money that they'll get paid out at the end of the experiment in order to try to get them to react strongly to things. After sort of calibrating their reactions based on this, we can then take this kind of simple model we learned by having them watching a game and actually use it to train a real robot. So we had this sort of simple like sorting task where the robot just starts by sort of taking random actions. It doesn't have access to any reward function at all. It's just trying to learn the task entirely from watching people's reactions to its behavior. And of course, this is super hard because people sometimes like have they'll anticipate, and so their timing of the reactions is like way off from like the event that happens, or they can anticipate something that never ends up happening. They can have paradoxical reactions where they smile when something bad happens. So it really takes quite a bit of effort to learn from this kind of data. But we have shown in this kind of proof of concept that it is enough to support learning even without access to any ground truth reward. Another type of uncertainty that robots have to grapple with if they're going to provide correct behavior with high confidence is state uncertainty. So this is another type of uncertainty that we've been looking at how to grapple with. And what we'd like to be able to do is something akin to like if you're trying to screw in a screw under a table where you can't see the hole. You're probably not just going to take your best guess as to where the hole is and then just try to go and insert straight in. You're going to instead kind of, feel around for it, wait for the screw to kind of fall into the hole a little bit. And once you're pretty sure it's in there stably, then you're going to start turning it. You're using a lot of like contact and force information to help localize and figure out what's going on. And robots are just pretty terrible at this kind of reasoning. And in fact, one sort of unfortunate thing in a lot of like the motion planning community is like contact's actually viewed as like this sort of bad thing that makes things hard, because now all of a sudden like you have these sharp discontinuities in your models, and it can be a complicating factor. But on the flip side, it also can provide landmarks and reduce your uncertainty. If you are up against a surface, with absolute certainty, where you are, in this direction, right? Which is great. So we've built a POMDP planner that can reason about uncertainty and use contact information, for example, to do two things. So in this example, what we're trying to do is insert some landing gear into a hole in the plane that from the robot's point of view, it cannot see. It even has noisy observations of where its own body is, in fact. And what our POMDP planner does is it tries to plan using contact to both reduce uncertainty and localize itself with respect to a known object, but also to break a plan into multiple pieces that are each of shorter horizon and that are broken at the contact point. And POMDPs are often, or just are exponentially difficult to solve in terms of horizon. And so if we can cut this horizon, by a significant amount, we can also make the planning problem much easier. And we found that these same ideas can be extended to not just contact, but sort of arbitrary changes in dynamics that we observe in the world. So for example, a stapler being rotational and then being pushed down far enough that it locks and becomes rigid. This is not contact, but it's a change in dynamics, much like contact is. So imagine that we wanted to take a stapler, for example, and pick it up off the table and put it on this tall stack of books. If the stapler was unlocked, the stack of books is high enough that the robot actually can't lift it up high enough to get it on top of the stack. And so like standard planners that don't reason about the object's dynamics will just fail. So what we do instead is, again, we kind of take a demonstration-based approach where we show the robot how the stapler works through this shadowing demonstration that allows it to feel all the forces that are being exerted on the stapler. And it notices like, oh, the stapler can be rotational. At some point, if you push it down far enough and hard enough, it locks and becomes rigid. And once it's learned a sort of kinematic and dynamics model of this object, we can then take that and plug it into our POMDP planner, and it'll come up with plans like this, where it sees that the stapler's open, it'll push it down onto the table and use it to both localize the stapler and to lock it so that it can then put it on top of the stack of books successfully. And here in these experiments, we actually hacked the perception a lot and sort of already assumed we knew about this object and could track it. But more recently, we've actually been trying to do these same types of experiments, but with raw depth data, both for generating point estimates about the kinematic properties of an object, and also more recently looking at how to actually estimate from depth information alone distributions over the model parameters of an object so that we can reason about sort of yet another level of uncertainty. Okay, so I'm just about out of time. I'm just going to really briefly just talk about kind of where I see this line of work going. So, my biggest goal right now is just to convince the community, both the robotics community and the broader like imitation and RL community, that value alignment's a first-class principle that almost every researcher should be thinking about. Nobody's going to want to use our algorithms if we can't guarantee they're going to do the right thing most of the time, and the success rate is just not the right metric. So it's going to be a hard sell though, because I think people think about value aligned learning or safe learning or whatever as just like slower normal learning, right? Like it's not going to, get the biggest number on the benchmark, that is going to get like your ICML paper accepted. So, I think there's going to be a little bit of a battle showing that, these algorithms don't have to slow learning. And in fact, we have some data in one of our papers about this method called shielding that, value aligned or safe methods can actually speed up learning because you're not wasting time doing stupid things. And so I think that direction is actually particularly exciting. I think we also need new benchmarks that actually reward people for giving, having algorithms that give guarantees, and then you have the benchmark check the guarantees to make sure they're correct, to get people away from just reporting success rate. And I think we have to realize that we're not going to get everyone on board. We're not going to convince Tesla they should only use value aligned learning algorithms to, improve their self-driving cars, right? And so we actually need methods that can verify value alignment efficiently post-learning and at scale. And toward that, we've been working, we just had a paper at ICML this summer about what we call sort of a driver's test for AI. That, when someone shows us, here's our self-driving car, if we want to evaluate how well it performs and if it's value aligned with us, we don't want to have to generate rollouts from, we don't want to just have to run the car out in the world and let it crash and do all kinds of terrible things and wait tens of thousands of hours until it starts seeing some of the edge cases. We just want something that's more like a driver's test, a really small set of directed questions we can ask that we think say something, hopefully provably, about generalization. And so we look at a bunch of theory for this and show under various assumptions and conditions how to construct these sorts of tests, which are very expensive to create. But once you create them, can just be deployed really quickly and at scale. Second, I think we need better human models. You saw a lot of equations like this today, saying people are either Boltzmann rational actors or rankers, but they're not, right? And if they're not, a lot of our guarantees actually just don't hold. So we need better models of how people operate, either truly modeling, like trying to model them by writing down things that we know about cognitive science and things, or data-driven type methods. And I'm running out of time, so I'll skip this. But essentially, we've been looking at one particular model of humans recently that shows that we can do much better learning from demonstration data if we assume that people aren't so much trying to be optimal, but they're trying to be information optimal and giving as much information as possible with their demonstrations. And finally, unsurprisingly, I want to keep pursuing this direction of multimodal data sources. In addition to the modalities I went into detail about, we've also been looking at things like, can we use videos of related but different tasks to help understand someone's intent? Can we use natural language if we have descriptions of the task, or narration during demonstrations, or verbal corrections when the robot makes a mistake? Can we use audio data? Like if we hear a click of one part going into another, what does that tell us about what's happening in the task? Or prosody data, if someone groans when they make a mistake, does that tell us something about what not to do, for example? And I feel like all of this is really just scratching the surface, and there's just tons more to be done on using every channel of data possible to really understand what people want. So to wrap up, if we want to get robots out in the real world, we need to address this value alignment problem. We have tons of literature on verifying behaviors with respect to known objectives, but there is not nearly enough literature on verifying that robots are understanding what we want and what our goals are with high confidence. And I think this is a really important area of research that I would convince all of you to at least take a look at and think about when you're designing your own algorithms. And that's it. So thanks to my PhD students who obviously did all the difficult work, and I'd be happy to take questions.
Well, thanks a lot, Scott, for the thought-provoking talk. So I think we have a couple of minutes for questions. So if anyone wants to pose a question for Scott. No? So maybe I'll get the ball rolling.
Sure.
So Scott, when you talk about these value alignment verification, are you still talking about these confidence bounds in some ways?
Yeah, so we're basically trying to say, once again, can we bound the policy loss within some epsilon with, like confidence 1 minus delta? And can we do that post-learning and with a very small number of questions? And it really depends on what you have access to. So like we have different methods for like if you have access directly to the robot's internal reward function to see if it's aligned. It might be a different reward function from like the ground truth one you want to match, or one that's elicited from preferences from a human, but it might produce the same type of behavior. Or maybe you only have access to, you have query access to like their Q function or their value function. Or maybe you only have black box access to their policy, and you can just say like, what would you do? What's the distribution of actions you would take at this state? And depending on the types of questions you're allowed to ask the agent, you have various either hard probabilistic guarantees, or in some cases only heuristic guarantees of generalization.
So is there some trade-off, or what about if the task is different or the task is the same but in a new environment, right? Which brings in the question of generalization. So
yes, so that is true. That the where we have to, in most of those cases, if not all, I have to think about that, but we do have to assume value alignment in an environment or distribution of environments. Things do get a little bit more tricky when you talk about environmental shift. I'm not, it's not clear to me that that's even theoretically possible to say anything like super strong about.
Yeah.
But that would be fun to think about.
Cool. So there's one more question from the audience. It says, what are the main challenges in using tactile feedback that you have run into?
Yeah, so the main challenge is that it's garbage. So, we've just used, force torque sensors in either the wrist or the joints of the robot, things like that. But, these things are super noisy. We'd love to be able to explore more with actually sort of high density, array tactile sensors on fingers and things like that. But, a lot of the commercially available ones are either, quite noisy as well. There's MEMS barometers that can be used, but you can't put tons of them onto a single finger. Or there are things like the gel site, which is super cool, but not widely available. Although some of you at MIT might have access to gel sites that are super cool. Some of them, like the Pneumatac, have to be filled with water and or saline and take a ton of maintenance that you have to deal with it. So I think that's the problem, and I think one of the most exciting areas of hardware robotics is really looking at how do we develop robot skin, essentially, that can do really interesting sensing, not just of normal forces, but of shear force, of vibration, of temperature. And when we have these more richer modalities, I think we'll be able to do much more interesting learning.
Well, thanks, Scott. I think, yes, getting good touch sensors is, all of us would really like to have them. So it would be great, to have them.
Yeah.
So